So we've seen how ETCS trackside can transmit a number of speed profiles to the onboard. We now need to look at how those are used by the onboard to establish what is known as the most restrictive speed profile. So how does it work? Well, as we've said, the trackside can transmit for each segment of the track a set of speeds, each of which has got one of up to about 30 characteristics attached to it. The ETCS onboard looks at its on-train configuration data, either supplied by the driver or as part of the maintenance setup, and from that information selects all of the profiles which could be relevant to the train. So how does it do it? What's the logic, and what does it generate? Well, the rules that are applied by the onboard start using the static speed profile. And V static is the basic speed profile. It has to be applied for the whole length of the movement authority, and it's transmitted as part of packet 27. Now, one thing we need to note is that each speed that's transmitted as part of the speed profile can be flagged as applying solely to the front of the train or applying to both the front and the back of the train. So, for instance, if you want to reduce speed on approach to a level crossing so the driver can see the crossing is clear, it might only apply to the front. But if you're going over a weak structure, speed needs to apply until the rear of the train has left the structure. So V static is the starting point. And the onboard looks at all the speed profiles to see if there are any which has a value of Q diff. This is a qualifier to identify the type of speed profile of 0. And 0 represents a Cant deficiency. If there aren't any, then the Cant deficiency speed is set to the static speed. However, if there are entries which show that there is a Cant deficiency, then the onboard needs to compare those Cant deficiencies with the ones which the train is capable of operating at. And if there is one which matches the train, then the speed associated with it, V diff, is set to the V Cant deficiency. However, not always do you get a perfect match. So if there is no match, the onboard then looks to see if there is another Cant deficiency curve where the Cant deficiency requirement from the trackside is less than that which the train is capable of. If there is, then that speed is used for the Cant deficiency and setting Cant deficiency to V diff. If not, we go back to using V static. So we now have a speed which is based on the Cant deficiency if there is one, and V static if there isn't one. And that is known as the basic Cant deficiency speed. That now inputs into the next part of the process, and here we're interested in the train categories. And these are denoted with NC diff. And the first question is whether there is a speed profile with an NC diff that matches the train for the particular segment we're interested in. If not, then the category speed, or the N speed, is set to the same as the Cant deficiency. However, if there is a match, then we look to see whether another variable, Q diff, is set to 1. If Q diff is set to 1, it means that we need to use the differential speed irrespective of what the Cant deficiency speed was. So a yes will result in V diff being used to set the Cat V. If not, then we look to see which is the lower of the two speeds, either the V diff associated with the train category or the current Cant deficiency speed. And depending on which is the less, is the one that is used. So let's have a look at a real example. We have a piece of track and we start in issuing speed information using the various packets. The start of the speed information is a distance from a reference point, normally the LRBG, and then is a speed. And in this case, the speed is set with Q front equals 1 to apply to just the front of the train. The next speed starts at a distance from the start of the previous speed and has other characteristics. And in this case, it is for the front and rear of the train. And so we can continue to create a speed profile, and this is the basic speeds. By adding one more at the end, another distance, we can cap the end of the speed profile, meaning if the train continues, it will not use any of the stored information. In addition, we need to consider what happens when a speed has Q front set to 0, as in the middle. Here, that means that the speed will extend by the train length. So depending on the length of the train will depend on where that speed actually is considered to finish, shown by the dotted line. We can now start to think about Cant deficiency curves. In the first segment, we've got two Cant deficiency curves. One for if a train is capable of 150 millimeters, and a higher one if it's capable of 210 millimeters. In each case, the speed is in kilometers per hour. And remember, the speeds have to be multiples of 5. And in the last segment, we have another Cant deficiency rated speed. In addition to the Cant deficiency, we can also have speeds related to train category. So in the penultimate section, we have one which is applicable to a freight train in G. And that one is one which is set with QDiv2, so it will pick whichever is the lowest speed. And in the last section, we can have one with a freight in passenger timings. Now, in addition to the profiles we've got here, although let's just add in the fact that the one in the penultimate section has Q front equals 0, so we need to remember that it extends into the next section by the train length. The dotted line is on top of the text. But in addition to this profile, all sent in the one packet, we can also send information about weak structures where the axle load is key. This is sent in a different packet. Again, it's referenced from the LRBG with a distance to the start, but in this case, each axle load restriction has a length. In this case, the restriction is to vehicles of C2 axle load or higher, and it is set for Q front equals 0, and so the speed is extended by the length of the train. If there's another axle load restriction, it is measured from the start of the previous one, not from the end, as shown, and has its own length as well. And this one is in the last section and applies to trains of D3 category or higher. So how does it all work? Well, let's imagine we have a freight train in the goods setting, so that's FG. It has an axle load of C2, and it's able to tolerate 110 millimeters of Cant deficiency. So we can start at the left-hand end. Well, if we have a look, we can see that it can't tolerate the Cant deficiency required for either of the two higher speeds, so they can be removed, leaving us with the basic speed profile for the first segment. Moving on to the next part, we can see that we have an axle load restriction, and since the train is of axle load category C2, then we need to apply that restriction. As we move across towards the right, we can see that we have got a section where it is applicable to a freight in goods setting. And since that speed is lower than all the other speeds, that one is going to be applied in the last section, penultimate section. And that will continue on unless there is a more restrictive speed. And in the last section, the only speed which is applicable is the basic speed profile. The axle load doesn't apply because it's for much heavier trains at D3. So now we have a speed profile for that particular train. And we can apply the same principles for a different train on the same track. Let us look at a passenger train. Here it has much lighter axle load, it can tolerate more Cant deficiency, and we also introduce the maximum speed of the train. And that brown line is set to indicate how fast the train can travel. And that is another constraint on the speed of the train. So again, we can start at the left-hand side. Here, the Cant deficiency of the train capability is 150. So we can apply the first of the Cant deficiency curves at 135 kilometers per hour. And that will replace the V static and the higher Cant deficiency will also not be used. So we have the speed for the first section. Moving on to the next couple of sections, the train is lighter than the axle load, so the axle load category will not apply. However, the V static is less than the maximum speed of the train, so the train will be restricted to the V static, including the dotted section on the end. In the next section, the train category doesn't apply because it's not a freight train, and the maximum speed that the train can travel is less than the V static for the majority of this segment, so that will cap the speed. Into the last section, we have a V static of 70, and that will be applied. So for our passenger train, we have a much simpler profile, a combination of the basic speeds, a Cant deficiency, and another speed capped at the maximum speed of the train. So what is these speed profiles used for? Well, the speed profile that we have generated is used to supervise the train. And of course, it's also displayed to the driver on the DMI. The speed profile on the left, which is inverted and twisted, is used to generate the planning area information of the speed that the train can travel.